we discussed about the membrane reactors, and then we mentioned that for membrane reactors, we have the reason is that there is a stream coming out of the reactor, so we need to approach differently by molar flow rate. That's what the whole argument of in this chapter was. And then we mentioned that for one of the components that goes out of the, excuse me. So for one of the components that goes out of the reactor, not only the inflow outflow is important, the transport phenomena is important. So thus you need to incorporate the mass transfer coefficient. So we came to this RV, capital R, which is the same kind of creature as a small r, but different meaning. So R has to do with the reaction, and capital R has to do with the mass transfer coefficient, right? So basically the reason that, like for example, hydrogen goes out of the membrane, so there is no more reaction. There is basically mass transfer coefficient. So that was where we stopped the other day. And mentioned that RB is WB times A, and this is flux. This is flux, and the small a is basically is the specific surface area meter squared per volume. Correct? That's what we stopped last time. Any questions so far? Okay, let's continue on that one, and then we do some examples as usual. And as your quiz is next week, so basically we're going to just do some more examples down the road, and next Tuesday get you ready for, I guess it's next Wednesday, it's the next quiz. So, do we have the same number of the quiz for other courses as well, or I'm the one that, you have 3 courses, right, in this, 3 quizzes. Quizzes are good, so make you ready. I mean, for the final, then you just remind yourself of what we did in the quizzes, and that will be the job. Okay, so WB would be K prime times CB minus CBS. CB is the component that goes out of the reactor, and CBS is the component in the sweeping gas, right? So this is the reactor, and then around this membrane. So the hydrogen goes out of the membrane, so then there is a sweeping gas either this way or this way. And generally speaking, this concentration is much lower than this concentration, maybe 100 times or something in that order. So therefore, you can, when it comes to the comparison between CB and CBS, you can ignore the CBS concentration. Again, we will do it in the examples. You will find out. So what is the unit of K prime C? This is the mass transfer unit, mass transfer coefficient. So the mass transfer coefficient, you can find out. This is C is the concentration unit, and the WB is the mass flux. If you divide up by each other, so would be you will end up with a meter per second, right? And this CBS is the concentration of B, is the concentration of B in the sweeping gas channel. In the sweeping gas channel. So Kc is the overall mass transfer coefficient, as I mentioned, is overall mass transfer coefficient. and takes into account this overall mass transfer coefficient, takes into account the resistance, the few resistance that we have, the resistance inside the tube, the resistance in the membrane. If you just remind yourself of heat transfer course that you have, you are having different resistances, right? So this mass transfer coefficient takes into account all kinds of resistances, including a tube side. Tube side means inside the tube. Membrane, and also shell side. So your A is the specific surface area, and is membrane surface area is membrane surface area over reactor volume. Reactor volume basically is meter squared over meter cube. If you write it down for a pipe, for a tubular pipe, what is the area, surface area of the membrane? Membrane is around the tube is pi d L, right? Correct. And what is the reactor volume? So it's pi d squared over 4, which is the area of the circle, times the length. So that would be 4 over d. Therefore, your RB, the component that stands beside a smaller r, is WB times A, and this is K prime CA CB minus CBS. So if you consider this one to be like KC, like it would be meter per second times 1 meter, so basically it would be 1 second. So that reminds you of the reaction rate constant for a first order reactions. So that would be RB. That gives you RB equal KC times CB minus CBS. KC has the unit of 1s, and RB has the same unit as the reaction rate, so it's mole per meter cube per second. And this CBS is going to be neglected most of the time. Any questions? Yeah, so it's average. And keep in mind that membrane diameter is going to be much less than this diameter. So like 10 times, 15 times, 20 times. So doesn't make a big difference, but we take the average. And after all, the resistance in an average the resistance of the mass transfer is an average of the resistance of the tube and the membrane and the shell side. So you are not expecting a lot of uncertainty by having an average. If you want to mathematically, I mean, just really do it. So you have to just take the integration, and then you need to have the mass transfer coefficient changing with respect to the diameter, and then take the integration. We are doing a lot of work for maybe a smaller percentage. And we don't know even because diffusivity and mass transfer coefficient by itself has 10% error. I mean, when you calculate, sometimes like density and viscosity, you can have a very good knowledge of the measurement. Like depending on the uncertainty of your equipment, you can have it 10%, 5%, even 1%. But when it comes to the transport coefficients, heat transfer coefficient, and specifically mass transfer coefficient, this uncertainty is huge. Like 20-25% is a good measurement. So therefore, we are dealing with this one. Then we want to just go like for 1%. This one, so measurements is already inside this uncertainty. Good question. Let's do this one in a couple of examples. So let's assume we have a reaction. A gives B plus C. Like the reaction can be like butane that gives butane C4H8 plus H2. So we do the mass balance, and let's assume that the B is the one that is like would be your hydrogen, the one that is going through the membrane outside. So if you do the mole balance would be a DFA, a DV is equal to RA, and DFB over DV is RB minus capital RB, and DFC over DV is RC. Then I write the rate law. The rate law would be RA is minus K CA minus CB CC capital C, which is an equilibrium constant. This is again, as we had before, is a equilibrium constant. Which is the ratio of is the ratio of R over RA over minus RA. And this is a rate constant. Okay, so this is your rate law. And if you remember, because you are dealing with a few rates, A, B, C, you need to have a relationship between RA, RB, RC. which you can derive from the stoichiometry. So basically your minus RA is equal to plus RB is going to be equal to RC. So then you need all these equations. So the good things or bad things about this chapter is that you write all these equations, but you will not be able to solve it analytically. So you need to solve it through the software. That's the reason I emailed you. Please go to the Wednesday to the workshop that you're going to do it for Polymath. Okay, did you get that email? Right. So with 1 hour we cannot do a lot. At least we can show you the interface of the software, and you should be able to know what is this about, because a lot of your examples in the book is based on the Polymath. 3 years ago when I taught this course, we had another additional hour. In addition to tutorial, we had also the lab, not the wet lab, it's dry lab, meaning that we had another 1 hour that I specified mostly for the software. But given the fact that we have very limited number for tutorial, so we cannot. I mean, I don't like just to specify for the software, but I like to just go there and see what is this, because this is a very user-friendly software, and you can also use it for ODE. So not only for this or for any other courses, for ODE, PDE, you can easily use that for rather than the MATLAB. So you can easily use that. And we can, if you need more information, just email us, and then I can provide you with the examples and other things with respect to this software. Okay? So next Wednesday, please go to the, not here, not to this classroom, go directly to the computer lab in the second floor of the B block. Okay, so the next one is relative rates. Relative rates, which would be, as I mentioned, is minus RA over 1 is RB over 1 is RC over 1. In other words, your RA is minus RB, and your RA is minus RC. So now additional equations that we have with respect to membrane reactor is a transport law, which I mentioned has to do with the mass transfer coefficient. So RB is KC CB, and then the next one is stoichiometry. Stoichiometry, and we discussed this one in detail in chapter 4. So just recall equations 417, page 116 of your book. If you remember, so we had Ca, the concentration of the A was CT0, the initial total concentration, times Fa over Ft. Ft means total flow rate, and Fa is the flow rate of the A. CB was CT0, FB over Ft, and the CC, the same things, so CT0, FC, FT, and obviously FT is FA plus FB plus FC. So you have done, if you do these stages, you are done. So from here on, you need to have the parameters in order to do it. So you can like if you wants to solve this one analytically, needs to combine all this equation, and at the end of the day, you are going to just have a very extensive nonlinear equation, which most likely you won't be able to solve it. You need to solve that one numerically as well. So if you want to solve that one numerically as well, so it might be a better and easier, more efficient approach to solve polymath. So parameters now. So let's assume that we have the parameters. So like CP0 is going to be 0.2 mole per d meter cube. So FA0 is 5 mole per minute. So K is 4 minute to the minus 1. This is rate constant. And Kc, the capital K is the equilibrium constant. So it's going to be 0.0004 mole per d meter cube, and Kc would be 8 minute to the minus 1, and this is mass transfer coefficient. So this one is mass transfer coefficient, and this one is the rate constant. Kc is the equilibrium constant. So the way that polymath works is just you define the equations as practically as you write it down on the piece of paper, and then you introduce the parameters, and then you mention solve. That will do it. And if there is an error in syntax or other things, we let you know. So you will find out it's rather user-friendly software. So the other mode of the reactors that it needs a specific consideration. Yes.
So I see that we have two different cases. I know it's a different value, like different numbers and stuff, but how are we supposed to differentiate them?
There are different, one is the equilibrium, one is the mass transfer coefficient.
But they're both Kc, right?
Well, I mean, one would be capital Kc, one would be a smaller Kc. I mean, in terms of distinguishing. So but they are hugely different. One is the mass transfer coefficient, one is the equilibrium.
The first one would be capital K.
So yeah, the equilibrium, usually in this course, we show equilibrium with the capital K. So far we have done this one. This one. And this one is the smaller K, which is the mass transfer coefficient. But they are, in the concept, they are quite different. Yeah. Okay, thank you. So the other mode of the the reactors that needs a specific consideration is a semi-batch reactor. So a semi-batch reactor is when you have either inlet or outlet coming to the reactor, and the other one is closed. So for the fully batch reactor, you don't have inlet, you don't have outlet. For semi-batch reactor, you have either inlet or you have outlet, one of those things, the other one is closed. So the examples that we give you in this course is mostly we add inlet. So we have a very slow addition of one of the components inlet, but the whole beaker or reactor is closed, nothing is going out. So the application of this type of reaction or reactor is when you have more than two reactions and the concept of selectivity comes to play. So when you have two reactions, so one of them mainly is desirable and the other one is undesirable. So that would be the target of our discussion in two chapters, not next chapter, the chapter after. So then the selectivity comes to play. The selectivity means which one of those 2 or 3 or 4 products are desirable and which one is undesirable. So you try to have the desirable advanced and undesirable not advanced. So one way to do this one is using the catalyst. Catalyst also does that. Catalyst not only reduces the activation energy and therefore the rate increases, but also tries to increase your selectivity, tries to make you have the better product that you like. This is another application of catalyst. However, in this discussion, we are not going to talk about catalysts. We are trying just to use the reactor, the semi-batch reactor, to enhance the production of the desirable product. Okay? So these few words that I mentioned demands a little bit of a definition for selectivity. So the title is a semi-batch reactor. Semi-batch reactor. And the reason we discuss semi-batch reactor, because not only we are going to just have a discussion on the selectivity, but this class of discussion needs a separate consideration than using the conversion. So you need to write the molar flow rate for each and every component and add them together. That's what they're all lumped in one chapter, in chapter 6 of your book. Okay? So the motivation to use semi-batch reactor is to enhance selectivity in liquid phase reaction. In liquid phase reaction. I'm going to flip the page, so if you don't mind. So the motivation to use the semi-batch reactor is to enhance selectivity in liquid phase reaction. And this is under the title of the semi-batch reactor. So I'm going to just, before going to the detail of the semi-batch reactor, I'm going to have a definition of selectivity. So definition of selectivity. You know, as the name suggests, so you have few products, and you want to single out or enhance one compared to the other one. So I'm going to just write it down. A plus B gives a D, and that would be a KD, and A plus B gives U, and that would be KU. Just for sake of argument, let's decide D would be desirable product and U would be undesirable reactor between these two reactions. Okay, so you can write the rate law for each of them. So rate of desirable reaction would be KD CA squared CB. And obviously, this rate doesn't follow the elementary rate law, otherwise you would have written CA times CB. Okay? So not all reactions are following the elementary type of reactions. So RU, the rate law for undesirable reaction is KU CA CB squared. This one also does not follow the elementary type of reactions because it doesn't follow the stoichiometry as a rate law. So we are going to define two selectivity. One is instantaneous selectivity, and the other one is overall selectivity. Both kind of emphasize the same things, but the definition is a bit different. Selectivity. And we have yield. Yield and selectivity are very close to each other in terms of definition. Yield is the ratio of the certain product compared to the initial one. So conversion, when we talk about the conversion, we are talking about the reactant. So you want to calculate what percentage of certain reactant is going through the reaction. This is the meaning of conversion. The yield is the similar one, but shows, you say, for example, the yield of this product. So it would be the amount of the certain product over the reactant. It's what I mean. The conversion is certain reaction over the whole thing. The yield is the product over the reactant. There's a small discrepancy. And the things that connects yield and the conversion together is selectivity. So selectivity, yield, and conversion. There's very subtle differences between all of this stuff. So selectivity means we call it S, and then subscript D over U means selectivity of desirable over undesirable. So it would be instantaneous would be RD over RU, R desirable over R undesirable. And the selectivity in the overall one, we put a little bit of hat on it just to distinguish between the overall and instantaneous. So it would be F, the molar flow rate of the desirable over molar flow rate of undesirable. Very, in definition, they are close. So the numbers do not match exactly the same, but not a big difference. So you can do, like, for example, one would be 70%, the other one would be 72%. So in that category. So the yield, we call it as a capital Y. So it would be RD over minus RA, and the yield of the little hat on top of it means overall would be FD over FA0 minus FA. So if you remind yourself of what was the conversion conversion was FA over FA0 minus FA. So basically is a ratio of the some certain reactant that is going to the reaction, but yield is the one that is produced. So this selectivity and yield, again, the reason we introduced now is because the semi-batch reactor that I'm going to explain it in a couple of minutes. So you need to understand the concept of the selectivity. Otherwise, in the chapter, chapter 7 or 8, we go in detail of when you are discussing the multiple reactions. Then this concept you will face over and over to solve these problems. Okay, so for this specific questions, for this specific questions, so SD, the selectivity of D over U would be KD CA squared CB over KU CA CB squared. And if you simplify this equation, would be KD CA over KU CB. So if you want to have a good selectivity of desirable over undesirable for this specific reaction, what would you suggest? What is your suggestion? To have a high selectivity of D, which is a desirable reaction. We should keep the concentration of A high, right, and CB low. If you want to have a good selectivity of desirable over undesirable, you want to have a higher concentration of CA and lower concentration of CB, right? Correct? Okay, so this leads us to the semi-batch reactor. So if you have certain criteria like these ones, what you do, you're going to have a lot of concentration of A sitting in the at time 0 in the beaker in your batch reactor, and you will start adding slowly, very slowly, B to the reactors. So therefore, you will keep at any given time the concentration of CB low, and since you are starting with a large amount of the A, always your CA is high. So that plays very well for this reaction. And obviously, if it was the other way around, so you switch the reactant. This is one of the applications of semi-batch reactor. Okay, so keep in mind this selectivity definition. Again, in a chapter or so, we are going to go very deep into this concept when we are dealing with 2 or 3 or 4 multiple reactions at the same time. Okay, so now I'm going to just, based on this concept, I'm going to just discuss briefly about semi-batch reactors. Semi-batch reactor. What is semi-batch reactor? So again, consider a reactor like this. So the reason we say semi, because we have inlet, we don't have outlet. So it's half batch in a sense. So you're going to have, initially you are going to have lots of A in your system, and it's a mixer that mixes the the reactant together, and then you add slowly B to the reactor. Okay, so practically we have in initial condition, initially we have CB0 is equal to CC0 is equal to CD, and that would be all to be 0. And the reaction that we are discussing is basically A plus B gives C plus D. This is the reaction. We are going to do a mass balance on every single of this reactant of A and B and C and D, and the difference for this semi-batch reactor is that similar to the membrane reactor, you have one component that is added as a transport properties, transport phenomenon. So the B that is you are adding it to the system, so it has two components. One component is that you are adding to the system, and the other component is when it takes the reaction. Right? This is the criteria of this chapter that we need to approach the design equation based on the flow rate rather than the conversion. That was the whole argument of this chapter, was it? Okay? So I'm going to do a mass balance on every component. Mass balance. Okay? So the mass balance on the A and B and C. So before going to the on each component, so we have dmdt, which is the mass flow rate of B is added here. Is going to be we usually in fluid mechanics you're familiar with m dot, so that would be rho 0 dv dt, and that would be dv over dt. If you are adding a constant rate of certain component, would be rho 0 times v0, and dv dt is v0. So if you have at t equals 0, your v is v0, so therefore your volume is initial volume, obviously, plus v0 over t. v0 is the dv over dt. So I'm going to use this equation as an additional addition to the when I'm writing the mass balance for the B, but for the A and C and D, we don't have the additional transport formula.